What I really would like to start with, and I want to say something about, the data is really the beginning of information. We take data and turn it into information. So what I'm going to provide you today is data and something to think about, something how this is going to work in your farm, your operation, how this is going to apply is up to you. One of the common things that I tell my students all the time is that the principles are few, the applications are many. Okay? How you work this and you apply this in your farm is quite a bit different than it would be perhaps even on your neighbor's farm. What I really want to talk about today, and this slide actually kind of drives home a little bit of the point, is a lot of the roots, getting to the root of this issue. Now, I also would like to just begin with a statement about funding, and some folks yesterday made some comments about funding and how university is funded. Let me just say for my projects, my efforts are funded by a lot of federal grants, very few industry grants, and usually if I do get an industry grant, I end up kind of making about half of them mad. Because they don't really like some of the data that comes out. So just so you know, this is unbiased. I try to be extraordinarily unbiased in this process. I grew up on a family farm as well. My dad and grandparents ran a 100-acre cow-calf operation. We also had a lime and fertilizer spreading business. So this is something that's very personal to me, and I really thrive on understanding more about this. And speaking of this, I'm in the education business. And to be an educator, you first have to learn, or you have to continue to learn, really. And so I brought my notebook along, and I'm always writing down notes. I've taken several notes while we've been here. And if you've got some comments or some experiences that you'd like to share, please add. Please add to the conversation. Okay, I want you to be engaged in this process. So let's talk about carbon to begin with. Where are the carbon stocks in the world? And this is on a global scale, and then we'll kind of work down to the very fine scale of in the soil. Most of the carbon is actually tied up, as one might imagine, in the tropical and temperate forests. Okay? A lot of carbon stocks are there, and it's a big chunk of our land area. A lot of that, of course, as a proportion, is going to be above ground. It's tied up into trees, into bushes, into aerial plant material. But there's also quite a bit that's going to be in the soil. In the soil. Now, grasslands are our biggest land use. Biggest land use worldwide is grasslands. And as a proportion, the majority of that carbon is going to be in the soil. Okay? And so if you look at total carbon stocks, actually grasslands are a major player there. So we need to understand the context of where our grassland agriculture, pastoral agriculture, fits into this scheme of things. Now, I'll show this later on, but I want to just give you some points of reference here. Here we are, and if I can hold my pointer still, right about there is where we're at. We're just below what we call the fall line, which separates the Piedmont area from the southern coastal plain, all along through here. So this used to be the coastline. Okay, so there's a lot of sand right in through here. And if you walk outside and you dig up a little bit of soil, it'll be mostly sand right through here. Okay, all the way over into Mississippi, and then as you get over into these areas, the organic matter starts to pick back up. But notice here in the Minnesota, Iowa, Dakotas, Wisconsin area, a lot more organic matter there. We're going to come back to that in just a little while. Now, I've already used two different terms. I've talked about carbon and I've talked about organic matter. And as I go through today, I'm really going to use those interchangeably. So think about them basically as being the same thing. Okay? The reason for this is we typically measure soil carbon as total organic carbon, or what we call loss on ignition carbon. Okay? Now, there are some exceptions to this. So those areas that have a lot of calcium carbonate in the soil, for example, maybe that may not be the actual measurement of organic carbon. But as a general rule, loss on ignition is what we're really looking at. So literally will put it into a device and they'll burn that soil, and what is burned off is carbon. Okay? What's left is the mineral amount. And total organic carbon contains roughly three things, and we're going to dissect those in greater detail in just a moment. Plant and root residues, that's the predominant compounds that you would see in total organic carbon, and then also humus. And then the soil microbes represent a huge portion of that as well. And what's interesting about that is they're doing all that work. They're cycling that carbon and allowing not only that carbon to be released, but also the nitrogen, the phosphorus, the other nutrients that are held up in that soil are being released. And the nutrients that are being held in that carbon is being released. Now, soil organic matter is 58% carbon. And so what we generally do, again, using soil organic matter and total organic carbon is essentially interchangeable, because to convert total organic carbon, this loss on ignition carbon, to soil organic matter, we simply multiply it by a factor, 1.72. Okay? Just so we're all on the same page here. Now, there are roughly four fractions of soil organic matter that we're going to make reference to here today. And the first one is the one that many of us have heard a lot about, is humus. Humus is the very stable portion of soil organic carbon that has been there for ages and is very stable. It will be there for ages more. The turnover time for humus is in the millennia, okay? Over the millennia, not just the shorter turnaround here. Similarly, it takes millennia to create humus oftentimes. It's going to take a long time. Now, there's a lot of debate about humus now, especially in the last 3 to 5 years. There's been a lot of research, a lot of science has gone into understanding humus a lot better. And what we used to think of as humus as being, we essentially separated it out by particle size, but now they're really beginning to flesh that out with carbon fingerprinting to be able to determine what is the source of that. Most of what I'm going to talk about are these other three things, because those are the three things that you and I can have an impact with within our lifetime. Within our lifetime, we're not going to do a whole lot about the humus, but we are going to be able to do a lot about stable forms of carbon that are in that soil. Okay, so plant residues, particulate organic matter, which is the partially decomposed plant material, and the hyphae of fungal mycelia, the seeds that might be in the soil, and then we have the soil microbial biomass itself, including bacteria, fungi, protozoa, and my favorite, nematodes. Nematodes, I think, are actually getting a bad rep. We think about those as being parasitic to plants, and there are certainly species that are. But nematodes also are the ones that are turning over a lot of the bacteria and the fungi in the soil. Okay? Let's do just a basic Soils 101 class here just for a moment on how do soils hold nutrients. Okay? If you look at a soil particle, let's take a clay particle for an example. If you look at a clay particle under a scanning electron microscope, what you would basically find is it's like sheets of glass that are laid on top of one another. Plates of glass-like material. And there's not a whole lot of surface area there, but along the edges, there's a lot of charge. There's a negative charge to that. A cation exchange capacity. In other words, the ability to hold on to cations, make it available to the plant, a cation exchange capacity of roughly 10. Now, organic matter, in contrast, organic matter has all these little nooks and crannies and all these little areas that are of surface area, where it has, again, negative charge, but not only just a little negative charge, it has a whole lot of negative charge. And because it has all this surface area and a lot of negative charge, it's able to hold on to a lot more nutrients than what the clay particle is able to, just because of its surface area and because of its charge. So organic matter may have a cation exchange capacity of 200 or more. Okay. So this is one of the reasons why it's so important for us to really improve organic matter in the soils. One is to hold on to more nutrients and make it more available to the plant. The other thing, of course, is it's like a giant sponge. That sponge there is going to hold on to a lot more water for us as well. Incidentally, I didn't share this with the other group yesterday, but 1 percentage point increase in organic matter holds roughly the equivalent of an acre-inch of water. Let me repeat that because that's important. 1 percentage point increase in organic matter holds roughly the equivalent of 1 acre-inch of water. Now, how many of you, as producers, and how many of your neighbors know that 1 acre-inch can sometimes mean the difference between a profitable year and a complete loss? Right? 1 acre-inch can make that much of a difference. And so 1 percentage point of organic matter can make a huge difference for us. Now, going back to this positive charge, if we look at all the macro, micro, and even these secondary nutrients as well, and again, things like ammonium, if we look at calcium, magnesium, potassium, many of these have positive charges, and there's, depending on who you talk to, there's either 15 to 17 different micro or different nutrients in general, macro, meso, or micronutrients that are important for plant development. Okay, so all of those are very important, and many of those have positive charges. Those that have negative charge are in the soil solution. They're in the water of the soil, generally speaking. Now, what factors affect soil organic matter? And Ray did a great job in the early session to talk about tillage. And we all know, I think intuitively we know, that tillage breaks down organic matter. Anytime we disturb that soil, we expose it to oxygen, we oxidize that soil. You know, it used to be that as I drove around in the spring of the year and I smelled that smell of turned dirt. I thought, my goodness, that is such a great smell. But actually now I've come to realize that's not such a pleasant smell. What you're smelling, incidentally, when you turn soil is the release of actinomycetes. Okay, so that is certainly, historically, has happened across our nation, across the world. So let's look at some studies here. This is soil organic carbon. Just don't get hung up on the units. Just focus on the relative differences here, because I'm going to use metric units and standard units as well. But notice here with conventional tillage and cropping, a survey of 29 farm locations across the southeast. Incidentally, Alan Franz-Lubers is one of the leaders in this area. He's an USDA ARS research scientist based now at NC State. He used to be at Watkinsville, just outside of Athens. Just a really great soil scientist and done a lot of work in this area. But notice here with conventional tillage, the soil organic matter, soil organic carbon is considerably lower than pasture. Okay, so this was actually cropped for 24 years and then put into pasture for 11 years. And they tracked the sequestration of carbon, or the addition of carbon, the buildup of carbon, and they looked at that rate, and in the top few centimeters, it's at a rate of 0.53 megagrams per hectare per year. That's a fairly considerable number, but we'll come back to that. That's actually quite low compared to some of the other data that we've been seeing. But nonetheless, we're adding a whole lot more organic matter to the soil by switching over to a pasture-based system. What about conventional till versus conservation till? Certainly, conservation till is a giant step in the right direction. I want to add something to what I talked about yesterday and kind of building upon something that Ray talked about earlier, is soil aggregates. You remember that slaking test that he was doing? Soil aggregation is essentially how those soil particles kind of glue themselves together and hold together. And the bigger those aggregates are on average, the better off you'll be in terms of soil structure and water infiltration into the soil. Okay. The mean weight and diameter of the aggregates, they get bigger. Okay, what this is saying is that those aggregates get bigger over time. That soil is healing itself basically from that tillage that has broken down those aggregates. If we look at water-stable aggregates, which means the slaking test, basically when you put it into water and if it slakes off, you can see that that does increase. Now what's interesting is, and what's not really clear is why this occurs, is why does that go back down after time? And I think probably what that is alluding to is the fact that we're dealing with essentially, in these were experimentally controlled to be just grass. No clover, nothing else, just grass. Okay? So I think that's part of what is going on there. Glomalin, I'm throwing some terms at you here, I hope you're not overwhelmed, but glomalin is the glue. Think of it as glue. Glomalin is the glue that is exuded by the plant roots and the mycorrhiza fungi in the soil that are holding those aggregates together. And even between grazing at a low grazing pressure versus high grazing pressure. Now these were continuously stocked pastures. These were not rotationally grazed. And I think if we were rotationally grazed, we would see that it would be much more on the higher end here. But even with high grazing pressure, notice here, high grazing pressure, we ended up getting more glomalin being produced. More glue, more soil glue is being produced with higher, what's going on there? With higher grazing pressure, we're getting more glue. Why is that? We're getting more root turnover. We're getting more root turnover. Let me give you another example. This is actually a cover crop that the producer was then harvesting that cover crop biomass and using that for baleage, and then he would come back and plant cotton into that. This was over near Savannah, kind of eastern part of the state. Let me fast forward to volumetric water content. That organic matter has a lot of water holding capacity to it. It holds on to, just like a sponge, it holds on to water. This tilled soil, relatively speaking, does not have the water holding capacity, the volumetric water content of our better mixtures here. Notice here that the annual ryegrass plus clover is holding about 20% more, 15 to 20% more water. Okay? Big improvement there. I would also submit, even though, and you have to forgive us on this triticale, in this particular site, in this particular year, that triticale stand was not very good. Now the triticale plus clover, it got better. But what I really want to point out is the difference between some of these better mixtures and the control, where there's nothing there planted at all. Now the porosity, normally we'd think of porosity being improved by having that more organic matter there. And normally we would, except for this has been tilled up, so it is more porous. The other big thing here is there's a lot of roots. This was a live sample that was taken, and measurements were made based on that. So when we measure porosity, you got to remember there's a lot of roots growing in this medium, in that soil, compared to the control that has been flubbed up. Now, what you can't see here is that about 4 inches there deep, it is hard as a brick. I mean, very hard. You can't, I had a garden trowel there and I was chipping on it. You know, that's how hard it was. It's like a brick. For that taproot to have broke through that, look how deep that is going, even through that severe compaction. You know, what Ray was showing there with the picture of that tree growing through a rock, we deal with something of that in kind of a microcosm as well here in many cases too. So some of these mixtures I think have some real advantages in breaking through that. And by the way, there's a lot of discussion about aerating soils and using an aerator to go through and aerate the soil to increase the or decrease the compaction and improve things. I would submit to you, and actually there have been tests that have been done that show that plant roots can go and overcome compression much better than any steel implement ever could. Okay? So if you focus on really improving the soil in terms of the nutrient or the root system, which also includes feeding it with some nutrients, then ultimately you'll end up breaking through a lot more of that compaction over time. Terry Chandler, I don't mean to put you on the spot here to point out one of our producers, but we were doing a field day over on Terry Chandler's place back, when was that, September or August, something like that, last fall? And you know, it was getting on the dry side. We were out there in the pasture, and there's great diversity there. And Terry was holding court over onto the side. He was talking about all the things that was going on, and I just happened to have my pickup truck there with my soil cone penetrometer. And a cone penetrometer is just a rod with a cone-shaped point to it, and it's got a tensiometer on it. So as you push down, it measures how much you're pushing down. So I just was walking around with that thing, and I was just pushing that down into the soil. Now, ordinarily in our soils, you get about 3 inches deep, and you just stop. You can't get it any higher. You can't get any deeper than that. And what I was finding is everywhere I stuck that thing, Carrie, I was going as far down as I could go with it. And you've been in a rotational grazing system there for how long now? 20 years? Okay? And if you corner him off to the side afterwards, he'll tell you what that farm looked like when they first started with it. It was pretty rough stuff. It was some of the most worn out crop ground that you would imagine. And you got to remember that in our part of the world, this area was cotton farmed to the nth degree in the 1800s and early 1900s. And when cotton was planted in that time, it was planted on 44-inch rows. Why? Because that's the width of a mule's rear end. All right? And if you've never been around cotton, it takes a long time for cotton to get relatively big, to canopy close up that canopy. So as it would go through the summer, it wouldn't really come to canopy closure until August or September. Okay? And the heavy rainfalls that we get sometimes would just come and then wash it out. And the theory is that we had approximately 12 inches of topsoil in this area before we started clearing trees and planting cotton. And the sad reality of that legacy is that when they would farm that land, they would run it out of topsoil, and because there was so much land west, well, they'd just move on to the next farm, right? And unfortunately, we haven't learned a lot of those lessons. How do we build organic? I would submit to you that the research is suggesting now that the most important factors are roots and root exudates. Now, much of what we have known historically, or what we thought we knew historically, was that it was just that leaf litter on top that decomposes, and eventually that becomes organic matter and eventually humus. Okay? Now, a lot of folks were taught that. I'm fortunate that in my career, maybe I'm a little different from Ray, and maybe it's a different era or something, but I was actually taught that the rhizosphere was very important. And if you look at the rhizosphere and talking about the roots and all the microbes, all the biota in that soil, the contribution of that portion relative to the above ground ranges from 1.5 to 3.7 to 1. In other words, the roots and the root exudates contribute 60 to 80% of the soil organic matter. Now, if you were taught that most of it's coming from the plant litter, it's definitely contributing. Don't get me wrong, and plant litter also helps to keep the temperature of that soil from getting too hot. But the majority of our work, and majority of our contribution can be coming here from supporting roots and root exudates. Ultimately, if you really look at the soil and what's going on in that soil, it's kind of interesting to see in a scanning electron microscope image here. Here's a little root hair. Root hair is coming off here. Here's a little root cap. All right, and it's exploring that soil. It's penetrating in between the little nooks and crannies of that soil. The other part that you see here, all this web, is not root. It's actually fungal mycelium. What we call our viscular mycorrhiza. Now, our viscular mycorrhiza actually enter into a relationship with the cells, the individual cells of that root. It will wrap itself around the cell of that root. It will feed off of the root. And the root actually gets some benefit from it as well, because the root is using that fungal mycelia to go out and get nutrients out of the soil and water and bring it back to the cell in the plant. So it's doing a lot of work. Yes, sir?
Question, when we're talking about, if we want to maximize soil carbon, are we better off letting the grasses get taller so the roots go down deeper, or defoliating quicker and shorter grasses?
Bear with me, because I'll get to that more, because that's exactly where I'm going with this. I will answer that. So if we think about what is going on here, we really have a whole complex system going on. We have a little ecosystem here in and of itself that we need to really focus on feeding. In fact, if you look at ryegrass, we grow a lot of annual ryegrass here in the state of Georgia, right? You've seen it driving up and down the roads and seen it on some of the farms that you visited. If you have ryegrass growing up about this tall, go out there and sweep it away. And look down at the very base of that soil, the base of that canopy, and look at what you will see. Now, it's a little hard to depict this in a camera image, But you see this down at the bottom? This is not just roots. There are roots there. Okay, there are some adventitious roots that are coming, they're popping out of that ryegrass. But there's also this web-like material, this fungal mycelia is actually colonizing those adventitious roots as well. Now, an old timer of our producers here in Georgia used to tell me, he said, you know what, when you see that, the purpose for those is because that ryegrass is growing so fast it's going to jump out of the ground if it didn't have that to root it in. That's pretty close to right. It is growing really fast at that point. And then you have these fungal mycelia that are living in conjunction with the root itself. Okay? They're actually wrapping themselves around the individual cells within that root. Another action location here is at the root cap, because the root cap is a source of many of the root exudates. And there are many things that are being exuded from that root to benefit the bacteria, so that the bacteria will do work for the root. There's also what we call root mucilage. Root mucilage, it's the snot of the soil. Okay? Nice. Yeah. You know, I've been hanging around Will Harris too much. So it is grease. It's lubing that soil area so that root can penetrate through. That's what it's doing. And really what a lot of it is sugar. It's sugar from root cells that have ruptured or been damaged in some way or been sloughed off by the plant as it's trying to exude. All of that is contributing to the organic matter in the soil. So if we can promote that, that's when we're really going to have a big improvement. But now, not all roots are created equal. Not all of these are created equal. What's really interesting is that when that root hair or whatnot will penetrate deep into that soil particle itself, into the little nooks and crannies, when that root dies back, either because it's grazed off above top and it's controlling its resources and it's dying back, but this becomes very protected soil organic matter. It's very stable. It doesn't change very often until you go in with a plow, until you disturb it. 25 years in this particular study. Okay? And what they were looking at is the rate of root production in terms of grams per meter squared, how much root is being produced, and the soil carbon change in a grassland environment here on their temperate steppes. This is their rangeland, their grassland. As root production increases, soil carbon improvements increases are linearly related. Okay? Linearly related. In fact, it explains about 80% of the relationship between them. So root production is extraordinarily important to soil carbon development. Root turnover, in other words, how fast those roots are turning over, also have an impact on soil carbon change. Again, a significant relationship here between those. Now getting back to our gentleman's point here about grazing and how do we graze to maximize root production? Well, what you don't see whenever a plant is grazed off is that the root system begins to die back a little bit. Now remember, those fine roots are kind of tucked away into the nooks and crannies of the soil, so they're kind of stable, so that's actually a really good thing. The problem comes in our continuously stocked pastures where they go back to the same plant over and over and over again and don't allow it to really regenerate its roots, is that those roots will eventually die back. And eventually, if you keep doing that, the plant will die completely. So if we give it adequate rest, we not only recover the top growth, but we also recover the root growth as well. And if we can set up this cycle, mimicking nature again, as going back to what Ray was talking about earlier, this is very similar to what goes on in the grasslands over time. She was growing these in a greenhouse, and you can see the PVC pipes here in the background where she was growing these in a greenhouse, and every 2 days she would come along and clip that one down to about 1.5 inches. Okay? Every 7 days she would come along and clip that one down to 1.5 inches. And then every 21 days she'd clip that one to 1.5 inches. Now this is a 4x8 sheet of plywood turned onto its side. And the bottom of that sheet of plywood is just off the screen here. So that's right there is about 36 inches, maybe a little bit more. Okay? Now, if you go back and look at a lot of the literature in terms of grazing, and growing up on a beef cattle farm, our backyard was our front pasture. So I spent a lot of time out there just watching cattle graze here, you know. I just love watching cows graze. They're fascinating. And some research where they've actually done that has shown that in a continuously stocked pasture, you open up the gates, you let them have at it, there's no rotation going on at all. On average, those plants are grazed every 2 to 7 days. So on average, those pastures have a root system that looks like that. Now, which one is going to be the first one to suffer from drought? Right? How much water are we actually going to be able to utilize? With the recommended rest periods, those roots will redevelop to approximately the same depth as those that have been uncut. Approximately the same depth as those that have been uncut. Now, if you get nothing else out of what I say today, I want you to leave you with 2 phrases that have served me extraordinarily well. The first is grass, post-grass. Post-grazing residuals are extraordinarily important. If you leave some grass, some green leaf area out there, you will grow more grass. It will be higher quality grass, and you will also grow better roots. Because good grazing grows great roots and better soil. Okay? This is a crucial point, and this is a story that we don't tell enough in the pastoral agriculture world. We don't tell this enough, and I'll get to that and what I mean by that in a moment. Okay, tall grass prairies, grasslands, bison, in this large ecosystem there. They go north during the summertime, come right back here during the winter. And large prairies of grassland have developed there over the years. And if you look at some of the work, and I know Alan Sater has been mentioned many times here, there's another good book too, and add to some of the ones that Ray mentioned, How Cows Can Save the Planet. We really can save the planet by using cows. Let me give you a case study as an example of that. Okay? We were looking at growth of our pasture-based dairy industry in Georgia. When I first came here, we had about 2 or 3 dairy farms that were really what I would consider to be pasture-based, okay, deriving at least 50% of their forage, their diet from pasture. And now about 20% of the dairy herd in the state of Georgia is on a pasture-based system. And in that 10-year time, or 9-year time, we've seen a pretty substantial increase in the number of pasture-based dairy operations, and we were seeing that they were using crop ground that had been cotton and peanuts, tilled. To grow peanuts, you literally have to dig them out of the ground. So those are tilled soils. And a colleague of mine, Nick Hill, happened to be on these farms and was working with them just before I arrived in 2006. And so he was taking some data off of those farms, 3 different paddocks. And on average, when they first started out, just after the conversion, they were at 1% organic matter, roughly. Within 3 years, they were 2% organic matter. And Nick showed me this data, and I said, there's no way. You're crazy. You didn't do this right. Something's wrong. The reason I said that is because this rate of organic matter development is like 3 to 4 times anything else that's ever been recorded in the literature. Okay? Why is this occurring? That's much kinder than what I actually said. There were a few obscene words that I won't repeat. I repeated them yesterday just because Will was in the audience. But this is what we looked at. We did what's called a chrono sequence. So what we did was we looked at some of these farms in various stages of development. And we had some that were just getting started and then some that had been in that system. In fact, we had a few data points, and we've taken those out because there were only 1 or 2 of those on the very end. We had some that had been in pasture-based dairy production for 20 years at this point. The rate of increase was exactly the same thing as what Nick showed me in that original data set. Here is what they started with in row crop and an adjacent farm. This is just one example. An adjacent farm. Now, after the first couple years, the 3rd year, and then by year 5, we're already seeing a tremendous amount of organic matter there at the soil surface. And what they were telling us is, after about 5 years, we don't really get the same response out of our nitrogen fertilizer anymore. We don't need to put on nearly as much. We're getting a whole lot more response. And what they're finding is they've jump-started that carbon cycle, that nitrogen cycle, and they were releasing a lot of the nitrogen. The highest other in the literature that we could find was 3 megograms of carbon per hectare per year. And we had trouble getting this published because no one would believe it. Because I didn't believe it. It's unheard of. Okay? The point is that we can do phenomenal things with this. And now in those pasture-based systems, we're increasing at such a high rate, I think we're going to plateau after about 10 years. In dryland pastures, what Alan's work has shown is that it really takes about 50 years to reach peak organic matter levels. Okay? Just because of the heat and humidity and the conditions that we have here are very conducive to organic matter decomposition. So that's about as high as they're probably going to go. And by the way, when folks first started showing up and clearing woods and converting it into cropland, our soil organic matter levels were roughly about 3 to 3.5. Some might be up around 4%. Okay? So what we're seeing is in those pasture-based dairies, we're getting up to about 4 to 4.5% after about 10 years. So it's a tremendous increase. And it may take us 50 years in some of these less intensive kinds of systems. Extraordinarily important. And earthworms are extremely important in this process, but also another creature is important for us. And in our pasture-based systems, I would argue that this one is probably about as important as anything else that we have. This is actually from NC State University, and I would encourage you, they've got a really great article on dung beetles, and really encourage you to go and read that for more information about dung beetle biology. Okay? Now, most of ours are going to be this type that are actually going to be incorporated rather than rolling off. We've all seen those the rollers in some of the nature shows and whatnot. Now, the dung beetle actually was excavating a hole underneath that and dumping out the soil over here. So I took a little garden trowel and I just flipped that dung patty over, and this is what we saw. Now, that hole was about the size of a soil probe. In fact, some of the producers that are kind of on the periphery, when they were coming over to see what all the excitement was about, they said, "You just stuck that soil probe in the ground." You know what? I didn't. That was the dung beetle that did that. In fact, that dung beetle hole, we took we had some long stalks off of that grass, and we stuck it down in to see how deep it was going, and it was about 8 inches deep, where that organic matter was being added to the soil. So, and I'm just going to report the data, and you decide, okay? Because this may be a little bit of a challenge to some of the thinking. Soil fertility has a huge influence on this role because we're feeding the roots ultimately. Okay? We're feeding the roots. Whatever way that may occur, if we feed the roots, we also oftentimes will increase soil organic matter. And they were looking at inorganic fertilizer, clover plus inorganic fertilizer, and then broiler litter. Okay? Using organic fertilizer for us, and this is in North Georgia, and that's our primary form of organic fertilizer, is broiler litter. Now notice here that they're pretty much all the same. Those lines don't have a slope that's significantly different from one another. Okay? Put a pin in that one, we'll come back to that thought in a minute. And in this case, they had both inorganic and organic forms of fertility. There were no statistical differences between the two, so they pooled it across the low fertility and the high fertility to look at that data. In the 0 to 1, there was a slight numerical difference, but not a statistical difference. But in the 1 to 3 inch increment, there was a significant improvement in organic matter development in the high fertility, as was in the 3 to 6. In the 6 to 12, there was a numerical but not a statistical difference. But when you pulled over the whole area here, 0 to 12 inch, there was a significant improvement in organic carbon by using higher levels of fertility. Whether that came from organic forms or inorganic forms, it did not make a difference in that regard. But the higher the fertility, the more organic matter is developed there. Now, this has been the holy grail of questions that I've wanted to answer for a long time. And I've searched the literature in the U.S. for ages trying to find an answer to this, and I really never found a good answer to it. And I found myself a couple of weeks ago in New Zealand, actually prepping for a tour that I'll talk about here in just a moment. But I was at a scientific conference there where they actually presented some data on this subject. This was actually published in Applied Soil Biology, Soil Ecology. Low phosphorus or high phosphorus fertility when they initially started this, okay, or just a year after, actually in this case, after they started it, and then in 2006. Okay, so a year after they started it, subtle but significant difference here between the two. In 2006, look at the difference in the numbers here of earthworms. Okay, this was with commercial phosphorus. Now, not to be undone, there was another study that they presented some results of at that conference that I was at in New Zealand. And this was all fertilization, not just phosphorus, 0, medium, and high levels after 38 years at a location there in New Zealand. And after 38 years, they had increased the number of earthworms. Now, I'm just going to leave that there, but my point is that they're really looking at feeding the roots. They're feeding the roots here. That makes a difference. This is a study that was done also in China. This is another one of those long-term studies, 25 years, where they were looking at what the initial soil was in terms of soil carbon using nitrogen fertilizer, commercial inorganic nitrogen fertilizer, inorganic NP and K based on soil test recommendations, and then manure with the balance of the nutrients being added as NP and K, and then just straw with NP and K. Okay, so they balanced it with NP and K, but they were just putting on residue there. So initially they had this number, but by just using nitrogen fertilizer, they decreased the soil carbon. And this is where some folks will just stop there. Okay, fertilizer's bad. NPK fertilizer, also, same sort of thing, they dropped it. And I'll show you the statistical separation here in a moment. But notice where they used manure and straw. The straw did not increase it, but it didn't decrease it either. But where they had manure and NPK in the top 8 inches, they increased organic matter. Okay. Now what about deeper in the soil profile? 8 to 16 inches. Go ahead and throw all of those up there. Same pattern. Going down deeper in the soil profile. Looking at building roots down deeper into the soil profile. If we're using dairy or beef manure, which is very high in moisture, those fresh pats are very high in moisture, that has an influence on what kind of biological life can be sustained in that period. You remember that slide where we were talking about broiler litter and inorganic fertilizer were not that much different? They were basically the same slope, same increase. I think a lot of that has to do with the fact that broiler litter is dry. There's just not much moisture to it. Going back to this, I think that fresh patty has a lot to do with the activity of those dung beetles. Okay, so let's talk about how those nutrients are redeposited, because our grazing management has an influence on where those nutrients are redeposited, right? Because if we don't manage our grazing and rotate those animals around, where are all those nutrients going to be? Right up near the shade and the water trough. Right? This is distance from water in the westerly direction and the north-south direction here in a 1 paddock out of 24 pasture rotation. The point here is that, yeah, you get a little bit around there, but you're getting a much better distribution here of those manure paddies compared to 1 paddock in a 3 pasture rotation, which is more or less a continuously stocked pasture. All of those nutrients are around the water trough or wherever the shade tree or whatnot may be away from it. They're camping out there. That's the thing, they're going to camp out there. Systems, it takes 27 years for the average square yard to get a deposition of nutrients through. Now, I'm a patient man, but 27 years is a long time to go between fertilizer applications. The 4-day will drop that down to 4 to 5 years. The 2-day rotation drop that down to 2 based on their estimations. Oh, that was kind of an interesting study. Now, not to be undone, the good folks over at NC State University did a very interesting trial in some of our pasture-based dairy platforms. And in dairies, in pasture-based dairies, they usually would get a fresh pasture after every milking. So once in the morning, once in the afternoon. So in the morning, they had access to the right-hand side of this pasture. This is the water trough and the gate. And then in the afternoon, after the afternoon milking, they'd have access to the whole pasture. Now, every one of those dots is a spot where a cow has either peed or pooped. And some of the poor little graduate students, technical staff, maybe even faculty members had to follow those cows around. And every time they peed or pooped, put a flag in the cow. And then come along and GPS all that in. Well, but what has resulted from that is a fascinating look at how uniformly distributed in one grazing that those nutrients are going to be. Okay? That, to me, is the story to be telling about grazing efficiency. And what they found was that only about 5% of it was actually captured on concrete. 95% of it was deposited right back onto the ground in some form or fashion. So how much can this really do? What would we do if we scaled that up? Now let's think about the degraded pastures, degraded fields, that where the organic matter has been severely damaged in the southeast. Now this is similar, you heard Ray's statistic that 23 million acres or something like that of prairie land has been converted over into to cropland. This is a big number here, but it's a huge, huge acreage. What if we just took 10% of that land and converted it to a pastoral system using this pasture-based management intensive grazing system as a model? So we're going to take 2.2 million acres and put them into pasture-based areas. What would happen? You know, we're academics. We can do some calculations to just see what would happen. What would happen? We would accumulate the equivalent of 4.5 teragrams of carbon. Now, teragrams is a huge number. Okay, that's like what is that? 9 zeros? It's either 9 or 12. It's a bunch of zeros. It's a lot of carbon. But to put it in real-world numbers, what does that equate to in terms of annual emissions? That's 3.5 billion cars worth of emissions for 1 year. That's as if every person in the world, or every other person in the world, had a car. Okay. 38.4 billion barrels of oil, or 4,332 coal-fired power plants. And in the U.S., we only have about 1,300. And that's at the end of 2012. And we probably have fewer now than we did even in 2012 with natural gas. So taking that number and plugging into EPA's calculator to what is the equivalent of that, that's what you end up with on the website. So parting thoughts. Now, in the agricultural world, and really in general in the U.S., I'm not sure, we have gotten scared of talking about climate change for some reason. And I don't understand why. Because we have a story that's very positive to tell. We can use pasture-based agriculture to substantially reduce our carbon footprint. Don't let anyone tell you that we cannot economically address climate change issues. Because if you're a producer in this room, you are economically addressing the climate change issue. Okay? That's my take-home message to you, is that we are making a difference. You're proof that it can be economically addressed. I want to share with you something that, to me, my trips to New Zealand, and I actually was trained by a Kiwi in the States. My major professor for my PhD was a native New Zealander. And the way that they utilize their grass in New Zealand is inspirational. It has really changed my understanding fundamentally of how to best utilize that grassland resource. And if you get a chance, and we hope that you would join us for this trip, to go to New Zealand and see how they're utilizing that. Not only how they're making great use of that resource, but they're doing it in a fairly sustainably way in many cases. Now, they've got their challenges, but what's interesting about New Zealand is their number one industry in New Zealand is agriculture. The great majority, greater than 50% of their national GDP comes from agriculture, mainly pastoral-based agriculture. Number two industry is tourism. But who's going to fly to New Zealand to see a bunch of polluted streams and whatnot? They won't do that, of course. So they've been very proactive about environmental constraints. And the producers have not always been happy about it, just like our producers are not always happy about it either. But they've been at the table. And one of the interesting things, one of the comments that has stuck with me during that trip is that he said, you know, I was at the table, I was part of that discussion. I felt like that if I wasn't at the table, I was on the menu. And he's right. And I'm telling you, you know, I get the privilege of dealing not only with producers, but oftentimes with some of the regulators. And I can tell you for a fact, you guys are on the menu. And if you don't engage, you're going to have some real challenges. Okay? Please, for your sake and for everyone else's, engage in that. What's interesting is that they have engaged in many cases here in some of what they call regional councils, which are regional bodies of basically watersheds that manage on a watershed basis. And each one of those watersheds have their own sets of rules, with some national rules that are kind of overarching, but they each have their own rules about regulatory issues. And many of them are engaging with the producers. And how they're engaging really sets a tone. Some of those producers, and one of the tourist stops that we'll visit is actually one who's doing research on their farm. They're bringing in folks to do research on that farm, paying out of their own pocket to set up grazing pastures. We were on one farm there that had replicated grazing pastures, just like what we set up on our research farms, just so that they could collect nitrogen leaching data, okay? So that they could contribute that data to the rule set so that they could modify it. And they've had positive influence on that. They've reduced the constraints there.